Good evening, everybody. Welcome to this presentation about an approach for automatic generation of the URDF file of modular robots from modules designed using SolidWorks. The authors of this study are Andrea Giusti, Renato Guidoni, and I, and this research has been carried out in collaboration of Fraunhofer Italia and the Free University of Bolzano. I would like to start with this slide by presenting you some main modular robots that we can find, and by pointing out also the difference and the main characteristics of modular robot. First of all, what do we mean as modular robot? So a modular robot is a robot that can be composed of different modules that can be assembled together in different order to obtain also different configurations. As we can also imagine, the main advantages of these modular robots is that a different and quick rearrangement of the robotic elements is possible, and obviously the robot is also able to adapt to different tasks. This means that depending on the task we are executing, we can find also the most suitable configuration of the robot to be exploited. And then also some damaged robots can be also repaired by adopting modular robotics. Then, as main disadvantages, we find that obviously each time the robot is reassembled, we need the time for its reconfiguration, but also programming skills that are necessary, and also the control obviously must be adapted. Well, as you can imagine, starting from these main disadvantages, we have tried to develop a kind of approach that is able to help the user in reducing the time necessary for the modular robot reconfiguration and the programming skills that are required. So we start our approach by designing the single modules we would like to have in a CAD software. And here we can find, for example, 4 examples of 4 modules. Then what we have done is to, starting from this 3D CAD software, to export each module to URDF format. In our case, we used the SolidWorks to URDF exporter plugin, and so SolidWorks has been the main CAD software that we have exploited for this study, as also the title of our paper mentioned. Then we establish a certain assembly order. So this means that starting from the modules that we have designed in 3D and we have exported to URDF, we established a certain order and the modules that we want to put together to compose our final modular robots. Once we have established it, we simply apply an algorithm that I will describe later in order to obtain the final unified robot description format of the assembled robot. So once we have the final URDF, we are able also to easily control the robot and to simulate also it. The great, let's say, advantage of this approach is that once we want to change one module or an assembly order, what we need to do is not to redesign the whole robot, but just simply to establish the new assembly order. And so once we have established it, we simply obtain the new URDF of the assembled robot. So we avoid the first 2 steps, and we simply repeat the loop starting immediately from the 3rd step. So in this way, you can imagine that the time and the programming skills that are required decreases a lot. Well, first of all, by talking about modular robotics, we distinguish 2 main modules, so the join module and the link module. Each module stores all the kinematics, dynamics, and geometry properties of the modules itself. So it's very important to have a correct, let's say, description of the modules in order to have also a final description of the robot. While the link module is a very simple part with just an input and an output connector frames, the join module is a more complicated one since it has 2 parts, so the proximal and the distal parts, always the input and output connector frames, and then we find the joint, which is the connection point between the 2 parts. So in modular robotics, we talk about modules, while with the URDF, we talk about elements. And so the URDF, which is the convention established within ROS standards, has the main difference to present two main elements, so the joint and the link elements. The joint element simply describe each joint with respect to a translation vector and a rotation vector with respect to the previous joint. And then for the joint element, we also established a type of joint and the axis of rotation and translation. The link element, on the other side, stores the dynamic properties, so by presenting, for example, the mass, the center of mass, and the inertia tensor that we have, so the inertial properties, and the visual and collision properties. And these frames are all presented with respect to the parent joint frames. Obviously, we should remember how, for example, more link modules put together could also lead to a link element. So, well, here I present you the models design and the established convention that we have exploited for our approach. For example, let's think about a link module. We want to represent it like this one in 3D, for example, and we want also to export it into URDF. But we cannot represent it directly as a single part, because when it has been exported to URDF, what occurs is that we just simply have this part. So this means that all the dynamics properties contained in the link module, they are arranged with respect to the origin frame, so 0, 0, 0. But we lose each information related to the output frame. But we want to also store this information, otherwise we cannot perform a further connection with the next module, for example. For this reason, in order to store also the kinematic properties related to the output connector, we introduced a virtual link, which is simple link, in this case a disk of negligible mass and geometry, but is also deleted in a second step. And so if we design the whole link module as an assembly, as a SolidWorks assembly in our case, the exporter is able then to detect the two parts as link element of the URDF, and the output connector is exported as a joint fixed. So this means that it doesn't add degrees of freedom to our module. That is what we want. For the joint is a bit more complicated since more parts are involved. So in this case, we have the proximal part and the distal part, which are connected together via joint, which in this case adds degrees of freedom since it's the revolute or continuous joint that we want to have in our module. And then at the end, also in this case, we add these output connector frames and a final virtual link that is always inserted in order to obtain the information about the kinematics and the position of the output connector. Here, obviously, we set always 0 just for sake of clarity, but each of these 0 must be substituted with the correct value of translation and rotation information. Once we have designed and obtained the URDF of all the single modules by following these standards, these conventions that I explained you, we simply implement an algorithm which is able to take as input the list of the URDF modules in the desired assembly order. Once we have indicated it, what the algorithm does is to create a final URDF of the final modular robots by starting from the URDF of the single module. And to do it, what it does is to delete all the virtual links that are present within the kinematic chain, and the only virtual link that is kept is the last one, in order to store the information about the last output connector that we have, and in order also to make it possible a further connection, for example, in the future with an end effector or with a next module, for example. This is the algorithm that I presented you, so just reporting in a more mathematical way. And so the final output, as mentioned before, is a URDF of the assembled robot, here indicated as XML, into a created ROS package. And then the algorithm, what it does is to verify whether the input module is a link or a joint module. And then at the end is change the child name. This means that if the output connector is as always as child link, the virtual link, this name is changed with, for example, the proximal link of the father joint element, or the link itself, the link module itself. So here you can see the results of our approach. So we start from different set of base modules, link modules, and joint modules. We established randomly different orders of these modules. And you see here the pictures that have been taken from Ervis visualizer in ROS of the final URDF that have been obtained. So for each image, we report, just for sake of clarity, the order of the modules that have been assembled together to obtain these 4 different configurations. There are only 4, but many other configurations obviously are obtainable. Here, so we realize some interfaces, just some graphical user interfaces to test also our approach. And you can see here, for example, from this brief video that I reported you, so we set as input a name of our robot, and then we choose the modules that we want to assemble. So a joint module, for example, or a link module, and obviously a base module, first of all. So here we select a link module, and we select the first one, and we just type finish the robot. So at the end, we obtain the final robot. Obviously, many other different modules can be added to this obtained robot. And we can visualize the URDF that has been obtained into Ervis visualizer. And as you can see, so a fast obtainment is possible thanks to this approach. And once we have it in URDF and into our simulator, it's also very easy to command it and to directly control it. Well, to conclude also this presentation, we would like to underline as a straightforward obtainment of modules from SolidWorks to URDF has been possible thanks to this approach. So our approach basically consists in this inserting of the virtual link as additional element in order to store all the information related to the output connector, and to make this reassembly of the modular robot to make it possible. Obviously, an high customization level of the modules is possible since you realize them in 3D. You can customize it as you want. Then these virtual links are exploited to perform the connection, and without loss of generality, only revolute joints have been considered during the testing step. But obviously, also their extension to prismatic joint is still possible. This approach has been developed for robotic arms, but promising extensions are also for mobile manipulators. Here, just for clarity, we can visualize a flowchart of the whole approach that I explained you in this presentation. And so starting from the design of the modules in 3D to their exportation into URDF by following the conventions, the design conventions, and then the synthesis of the robot's URDF from modules by applying the algorithm that I explained you, and then at the end we obtain the final robot's URDF. This is everything from my side, so I would like to thank you very much for your attention, and thank you from my side and from the side of my colleagues. And if you have questions, I'm very glad to answer you. And obviously here you can find also our contacts. Thank you very much.